Assalamu alaikum. In today's lecture and in next few lectures, we shall talk about the fundamental principles which govern the working of AC machines. We shall start with the simplest case, that is a loop of a rectangular loop of a wire rotating in a uniform magnetic field created by two poles. In the first part of this lecture, we shall derive the expression for voltage induced in this coil, and then we shall derive expression for torque induced in this coil. The arrangement over here is simple. We have north and south poles, and there is a rectangular coil which can rotate about its axis. If we look this arrangement from the front, we have this front view. We have north and south pole, and there is a uniform magnetic field due to these poles. And if we look this arrangement from the front, only this side of the coil will be visible. The orientation of the coil depends upon time, since it is rotating, so at different time instants it can have different angular position. So this is general position, and these sides of the coil, these can be represented by these small circles. The back side of this coil is not visible if we are looking at the front view. A similar arrangement we have already talked about when we were discussing fundamental principles governing the working of DC machines. Over there we had this situation. Again we had north and south poles. However, when we were talking about DC machines, there were certain differences compared to this arrangement. Here the pole faces are flat, and over here the pole faces are curved. And in this case, in the case of DC machines, the coil was placed on a cylindrical rotor of a ferromagnetic material. Over here it is placed in the free space. So the situation in this case was like this one. The flux lines emerging from the north pole, they reach the south pole, and the flux lines, you already know, these follow the shortest reluctance path. So this was the path followed by the flux lines. So over here these flux lines were not straight lines, rather these lines were always perpendicular to the surface of the rotor. That is, when we had this linear velocity of the conductor, the flux lines were always perpendicular to the velocity. This was flux density, and this was the velocity of the conductor. So at each time instant, velocity and the flux density vector, these were always perpendicular. The situation over here, since we have a free space, so flux lines, we have uniform flux lines. However, what we can see is that if this coil is rotating in this direction with angular velocity omega, this is linear velocity of this conductor, and the velocity vector in this case is not perpendicular to the flux density vector. So these are the differences with this situation that we discussed earlier and this one which we are going to discuss now. So let's derive the expression for voltage induced in this coil. This coil, you know, is a rectangular coil. Let's name each side of the coil. We have this rectangular coil with four sides. This side is named as side AB, this one side BC, and this one side CD, and this one is side AD. We know that a conductor moving in a magnetic field, a voltage is induced in that conductor, and the expression for induced voltage, you already remember, is given by V cross B dot L, where V is the linear velocity of the conductor V is flux density, and L is the length vector, as we already talked about. So let's see what is the voltage induced in each side of this coil. We start with side AB. So side AB, voltage induced in side AB. Here this is side AB. So velocity of this conductor, linear velocity, VAB. So this is linear velocity of this conductor. What we can see is that this velocity is not perpendicular to the flux density vector. Rather, there is an angle between the two. Let's name this angle as theta AB. Therefore, V cross B is VAB multiplied by flux density vector V, and then sine of the angle between the two quantities. So V cross B is VB, VAB, and sine of the angle between the two vectors, and then dot product of this vector and this vector. What is direction of this vector? This direction of V cross B. Direction of V cross B can be determined in several different ways. The simplest one is by the grip rule. If we rotate the first vector in the direction of second vector, then the thumb will indicate the direction of their cross product. So V AB cross B is into the surface of the board. That is in this direction, which is then parallel to the length vector. This side is placed like this one over here. So V cross B is also in this direction, L is also in this direction. Both are parallel, therefore their dot product is simply equal to VAB flux density vector of magnitude of the flux density, VBL sine of the angle between the two. And what is polarity of this induced voltage? Polarity of this is into the surface of the board. That is, if we allow the current to flow through this coil, it will flow into the board. That can be denoted by cross notation. So current, direction of current is from here to here. Next, what is voltage induced in this segment? Segment BC. So voltage induced in segment BC. Again, the cross product of this velocity vector and this flux density vector is into the surface of the board, which becomes perpendicular to the length vector. This back side of the coil, this side over here, and then this is direction of the cross product of V and B. So this cross product V cross B is perpendicular to the length vector, therefore their dot product becomes equal to 0. Dot product of V cross B and L. V cross B, direction of V cross B is into the surface of the board, and direction of L is here, this conductor. So the two vectors, that is V cross B and length vector, these are perpendicular to each other. Therefore, no voltage is induced in this segment. Similarly, the same discussion for this side, EAB. The same will be the situation over here. Length vector will be perpendicular to the cross product of V and B. Therefore, no voltage is induced in this segment. Now we talked about segment CD. This coil is rotating in this direction, so this is linear velocity of conductor CD, VCV. This is direction of velocity. I sketch it over here. This is velocity vector and flux density vector, and the angle between two vectors is theta CD. So this VCD multiplied by this cross product is this vector, magnitude of this vector multiplied by magnitude of this vector into the sine of the angle between two vectors, and then dot product of this resultant vector with the length vector. So what is direction of this vector? We can again determine the direction by this grid tool. Rotate the first vector in the direction of second, then thumb will indicate the direction of their cross product. That comes out to be out of the surface of the board. That is this is out of the surface of the board, which can be denoted by this dot notation. This V cross B is then parallel to the length vector. This conductor is placed like this one. So V cross B is also in this direction. So V cross B and L are parallel. So we have V C D B L sine of the angle between this vector and this vector. What we further observe is that this velocity, linear velocity of this side of the coil is the same as linear velocity of this side of the coil. So let's call it V. So we can just omit the subscripts over here and as well as over here. Furthermore, this angle CD is related with this angle theta AB. How this is the if I redraw this diagram over here, this is the situation V AB, and then this is the flux density vector, this is angle theta AB. I have simply redrawn this diagram over here. What is this total angle? This angle, this is 180 degrees, and this angle is 180 degrees minus this angle. And what we can see is that this angle is the same as this angle by simple trigonometric relations. That is, theta CD is equal to 180 degrees minus theta AB. This angle is total 180 degrees minus this angle. So this angle is the same as this one. So theta CD is 180 degrees minus theta AB. Therefore, this expression this is equal to VBL sine of 180 degrees minus theta AB. What we further notice is that sine of 180 degrees minus theta, that is simply equal to sine of theta. You can just verify it by using the trigonometric relations that you already know. That is, sine of this thing is sine of 180 degrees into cosine of theta minus cosine of 180 degrees multiplied by sine of theta. So this sine of 180 degrees is equal to 0. So cosine of 180 degrees is minus 1. This minus 1 multiplied by this minus is plus 1. So this expression is simply equal to sine of theta. Hence, this voltage, induced voltage, that is equal to VBL sine of theta AB. So what is total voltage that is induced in this coil? That is a sum of the voltages which are induced in all these segments. What we can see is that the polarity of voltage induced in this conductor is this one. In this segment, it is out of the surface of board, that is coming out of this wire. This one is the polarity of the voltage. The two voltage sources are in series. Therefore, total voltage that is available at the these wires of the loop, that is sum of this voltage and this voltage, because no voltage is induced in this segment as well as in this segment. Hence, the total voltage induced in this coil, that is equal to 2 VBL sine theta. We can even omit this subscript AB. So this is the expression for voltage induced in a coil rotating in a uniform magnetic field. Let's rewrite this expression in a form which will be more convenient when we shall be talking about real AC machines. So let's rewrite this expression. Here theta is the angular orientation of this coil that is related with angular velocity. We know that theta is equal to omega t. Furthermore, this linear velocity of this conductor, that is also related with the angular velocity, that is V is equal to R omega, where R is the radius, this length is the R, this length is R. Therefore, this expression for induced voltage, that is, what is this thing? 2R is this length is 2R. What is this length? Is this length. So 2R multiplied by L is the area enclosed by this loop. So let's replace it with area, where this A is the area of this loop, which is equal to 2R multiplied by L. So what is flux? What is the flux which is passing through this coil? At different time instants, different flux passes through this coil. It depends upon the orientation of the coil. Maximum flux passes through this coil when this coil is at this orientation, and minimum flux will be passing through this coil when it is in this orientation. And at other times, the flux which is passing through the coil, that is changing. So what is maximum flux that will be passing through this coil? We know that flux is flux density multiplied by perpendicular area, and maximum flux will pass through this coil when it is just perpendicular to the surface of this coil is perpendicular to the flux lines. In that case, maximum flux will be equal to flux density multiplied by area of the coil. So this thing A multiplied by B, that is the maximum flux in the that is passing through the coil. So this is the expression in more refined form for the voltage induced in this rectangular coil. We can see that we are getting sinusoidal voltage signal out of this coil, and the magnitude of this voltage signal, that depends upon maximum flux that passes through the coil, and it also depends upon the angular velocity of the coil. That is also the situation in real AC machines. We shall talk about real AC machines in later lectures. Over there, we shall also observe that the same expression, similar expression for voltage induced in those machines. Remember that this is not a real AC machine. Why? There are multiple constraints over here. Here we have air space, free space, and we need very strong magnets to cause the flux to flow through this free space. And we see that the magnitude of this voltage depends upon the flux, somehow depends upon flux density as well. So to induce some significant voltage in this coil, we need very strong magnets if we have a free space. So this is one reason for this machine not to be practical. Furthermore, how we would connect the electrical load to this coil? If we just connect a load to this coil we know is rotating, so this wire will twist and finally it will break itself. So the strategy that can be utilized is that of slip rings. That is, we have this coil. So to get electrical signal out of this loop, we have this arrangement. We have two rings. One ring is connected with this side, and the other ring is connected with the other side. This wire is insulated from this ring, and with this arrangement we can get electrical signal out of this loop, and therefore we connect electrical load to this thing. Remember that this arrange of slip rings, that is different from the one that was discussed when we were talking about DC machines. Over there, we had this situation. We had these half rings, and these rings were connected to two sides of the coil, and then there were brushes over here. And at certain time instant, this side of the loop, that is this slip ring, was connected to this brush. At next time instant, this segment of the slip ring will become in contact with this brush. Over here, the same slip rings remain in contact with the same brush always. Here, the objective was to get a unidirectional voltage signal out of this loop. Here, we want to have a bidirectional voltage signal out of this loop. So this arrangement, this mechanical arrangement, moving parts, that is always problematic, and that was one of the major problems with DC machines. We would also like to get rid of this arrangement in real AC machines, as we shall talk later. In the next part of this lecture, we shall talk about the voltage, the torque induced in this coil placed in a uniform magnetic field and carrying a current in it.